So linear equation, which we have forcing function of ft in piecewise continuous, like illustrated in previous figure. So one of approach is differential equation, which having such a forcing function is to solve the separate for each of the continuous component. So for example, we have f1 and f2, so and so on. So using the fact that the equation all derivatives except the highest must remain continuous, so that the value of the point of discontinuity provide initial condition for the next station. Okay, so this approach is obviously rather tedious and much more direct. One is to make use of Heaviside step function to specify of the function, and the method solution follows as examples. Okay, so for examples, in example 5.0, so we obtain the solution of x t, which is t starting from 0, of the differential equation. So this is differential equation. We have second order of differential equation. Okay, d square x divided by dt square plus 5 dx dt, the first differentiation, and the normal functions as a ft. So from this question, we know that the ft has a pulse function or limits of two conditions, which is the function will be 3, ft equal to 3, when your t from 0 to 6. Okay, so the moment t is above from 6, okay, 0 to lesser than 6, okay, and t equal to 6 and above, the function will be ft is 0, which is subjected to initial condition, which is x naught equal to 0 and x dot naught equal to 2. Okay, so what you need to do now, we have two conditions here. First, the condition from 0 to 6. Okay, the second condition from 6 and above. Okay, so we go one by one. So for 0 to lesser than 6, okay, the functions, this is the main functions, can be transformed into Laplace transform. Okay, so we know that previously we learned in differentiations, okay, when you have dx square, okay, your Laplace transform will be like s x bigger x s square minus s x node n xs x node, okay, minus x dot node n. Okay, okay, so this is for d square over dx. So there's the second one will be dx over dt. So dx over dt we have learned previously. So your function will be 5 times s x bigger x, sorry, xs, okay, minus x node. Okay, okay, so both of the function and also 6x will be separated. On the left side, you remain the s square x function, xs function. So you will have x square. So this is x square. The second one you have 5s, and second one, this one will be 6s, 6sx. So it will be 6 here. The rest, okay, you have this one, yes, this one, and this one will be on your right side. Okay, so when you put it everything right side, plus with the 3 here, okay, so we can Laplace it. Okay, this one it become s square plus 5s plus 6 times x bigger xs equal to sx node, x plus x dot node plus 5x node, and the 3 when we Laplace 3 become 3 over s. So we know that x node equal to 0, so automatically this one will become a 0. Okay, then x dot node become 2, then this one becomes 0. So that's why you will get this one, which is 2 plus 3 over s for this Laplace. Okay, from here you can simplify it to be x on the left side So that's why you get 2s plus 3 divided by s. Okay, how to get this one? You need to separate it into a, so before you go for partial fraction, this one is partial fraction, you need to separate this one. Okay, for example, you have s squared plus 5s plus 6. This one can be factorized, become s plus 3 and also s plus 2. Okay, so this one, that's why you have okay, and then you have this 3s, so you denominator, you make the denominator is equal, so you have 2s plus 3, s plus 2 and s plus 3. Next is you need to do the partial fractions, so you get the constant of a, which is 1 over 2s, plus constant of b, 1 over 2s plus 2, and minus 1 over s plus 3. From here, we need to do the inversion. We call it inversion. Inversion means you have in the Laplace transform towards the function of t. So we call it as inversion. Okay. This is inversion. So when you inversion this one, okay, we know that 1 over 2 become constant, over s become 1 over 2. Okay, 1 over 2 s plus 2 become 1 over 2, s plus 2 become exponent negative 2t. Okay, then minus 1 over s3 is exponent minus exponent negative 3t. So in your inversion, in the range from 0 to t to 6, okay, this is your inversion point. Xt is equal to 1 over 2 plus 1 over 2 exponent negative 2 minus exponent negative 3. Okay, so we know that, okay, we have the inversion, main inversion of equations. So we know that the limits is from 0 to 6, 0 to 6 and 6 and above. The next, the 0 become the initial. The next is in between is a 6. So from here, we should determine the value of x6 here, okay, and x dot 6 in order to provide initial condition of the next stage. Okay, the first initial condition 0 to 6. The second initial condition is 6 and above. So you need to select 6 as the main t. Okay, so in this case, when x t, when x6, so you just change the t into 6. So you will get 1 over 2 plus 1 over 2 exponent negative 12 minus exponent negative 18. So we can put it this one as a alpha. Okay, and x dot 6 say is negative exponent negative 1 over 2 plus 3 exponent negative 8. So we call it as a beta. Okay. Okay. So if you not this one is based on the previous function xt. Okay, x dot is a differentiation of xt just now. Okay, x dot is a differentiation xt. You need to differentiate first, then put t equals 6. In this case, xt, you just change xt when t equal 6. Here you need to differentiate, then you put the 6 here, then you will get this one. Okay, so in order to do that, we simplify it to put it as alpha for x6, and x dot 6 we put it as a beta. Okay, for t is bigger than 6, so we need to make a change where is your t equal to t small t minus 6. Okay, so when your main function is under big T, so this function with d square x divided by dt square plus 5 dx divided by dt plus 6x is equal to 0, where is your t is t minus 6. Okay, so subjected to x t equal to 0 is alpha, and x dot t equal to 0 is beta. So this one, same procedure. You need to taking the Laplace. So based on the Laplace, we get a same one, s squared plus 5s plus 6 times x bigger xs. Then the second one, x sx note, and s x note then actually. But now it become s t big T equal to 0 lah. So x dot t equal to 0 and fx t equal to 0. So we know this one can go for alpha. Okay, this one will be a beta and alpha and beta. Okay, so your function can be simplified is alpha s plus 5 alpha plus beta. Okay, so this one will be beta, this one will be beta, this one will be alpha, and this one will be alpha. Okay, based on this condition. Okay, so from here, you will get the function in terms of alpha and beta. So which is your xs, you bring this one to the right side, okay, divided by this one, simplify it, okay. So you have s plus 2, s plus 3 for the denominator. So your function will be alpha s plus 5 alpha plus beta equal to s square times, sorry, s times 2 times s plus 2. So from here, you need to do your partial fraction. So in this course, you need subject, you need to be good in partial fractions. Then you will get beta plus 3 alpha s plus 2 minus beta plus 2 alpha s plus 3. Okay. So next is from here, this is under Laplace. So we need to transform for inversion. Okay, inversion. So from xs to xt. Okay, so inversion. So okay, I just put it here for you to easy for you. X s is equal to beta plus 3 alpha divided by s plus 2 minus beta plus 2 alpha divided by s plus 3. So in order to do the inversion, you need to inversion to xt. So we know that 1 over s plus 2 is exponent negative 2 times the constant b beta plus alpha minus plus s plus 3, 1 over s plus 3 is exponent negative 3t, a big T. In this case, big T. So times the constants is beta plus 2 alpha. Okay, so you have already the inversion of this one. So based on this inversion, we know that previously our alpha is this one. This is our alpha. This is our alpha value. This is our beta value. So you just insert substitute the alpha and beta value in the alpha. Okay, alpha plus 3 alpha. So simplify, it becomes something like this. Okay, exponent negative 2t. Your t in this case is t minus t6. Small t minus t6. So you change t minus t6. So here you need to change your beta. Okay, change your beta. Okay, change your alpha and change your t, which is your t minus 6. So you put it, what is beta alpha? You will get this one. Then negative 2t, the big T is equal to t minus 6. You just change to t minus 6 minus beta. Okay, put the value of beta plus alpha plus 2 alpha. You simplify, you will get 1 plus exponent negative 18. So exponent negative t, the big T change to t minus 6. So this is condition from t is bigger than 6. So when you simplify, you will get something like this. Okay, these conditions. So once you have this second condition of t is bigger than 6, so you can go for the limits, what we call it, the pulse functions. Okay, so this one is based on 0 to 6. So this one you are taking this one. Okay, so this is from 0 to 6. Okay, you can see 0 to 6. Okay, 1 over 2 plus 1 over 2 exponent negative 2t minus exponent negative 3. So we put 1 over 2 plus 1 over 2 exponent negative minus negative 3. The second, from t above than 6, you need to, based on this function, okay, based on this inversion function. So where is 1 over 2 exponent negative 2 minus exponent negative 3 plus 3 over 2 exponent, okay, this one is similar one. So that's why you will have this final inversion conversion of differential equations. Okay, so from here, what you can see here, this one is in terms of ft, the first function ft, where is your first function ft, when t from 0 to 6 is 3, from t above 6 is 0. So you can see the graph is from 0 to 6 is 3, okay, from 6 and above is 0, okay, is 0. Okay, when we already doing the inversion or differential equations, the equation will be something like this. So this one will be when 0 to 6, the equation will be based on this one. You change t equal to 0, what happened, so you get this type of graph until here. Okay, from 6 and above, you use this equation, so you will get another graph something like this. Okay, so this is for xt function. This one is a ft function. Okay, so that's the first method in order for you to solve the differential equation. Okay, here is the second method. Okay, so you can use the Heaviside step function method. So we know that ft, okay, equal to ft. Okay, this is our main function. Okay, ft is based on 3 when 0 to 6. Sorry, t 6, and 0 from t is above than 6. So this is your function. So from here we can use the Heaviside step function. So where is your Heaviside step function will be ft is equal to 3, this is your constant, times the Heaviside step function ht, so which is t0, then minus 3, the constant h, where is your t? T minus 6, so limit is 6, t minus 6. Okay, you can see from the previous notes I taught you. So this is your function here in Heaviside step function. So what happened here when you Laplace this function? Okay, so 3ht will be 3s minus 3ht minus 6 will be 3 over s exponent negative 6s. Okay, so when you get this one you need to base, okay, this is the simplification of the Laplace, so you need to base on the equation again, okay, the function, okay, which is this one. The function will be d square x dt square plus 5dx over dt plus 6x, okay, is equal to the function. In this case, our function will be Laplace of ft, which is 3 over s minus 3 over s exponent negative 6s. Okay, so here you need to do based on the Laplace transform of this one, similar like previous. So we get something like this. Okay, then with our conditions, so this one will be 0, this one will be 0. Then plus the function of Laplace on the right side. Okay, so plus this one. So that's why this one will be 0. This one will be 2. Based on the condition will be 0. So when 2 plus Laplace, the function is this one. So you get 2 plus Laplace. The Laplace is 3s minus 3s exponent negative s. So you get the same function. So you need to simplify from here, factorize. So you will get something like this. Okay, then this one will be partial fraction. So you will get something like this. So you have 1 over 2s plus 1 over 2s plus 2 minus 1 over 3 plus minus exponent negative 6, the constants. Then partial fraction, this one will be 1 over 2s minus 3 over 2s plus 2 plus 1 over 3 s plus 2. Okay. So taking from here, you have the next step is from xs, you need to inversion of Laplace become xt. So we know this one 1 over s become 1 over 2. This is 1 over s 1 over 2 exponent negative 2 t minus 1 over 3 become exponent negative 3 minus this one will be step function. Okay, this one will be a step function of ht minus 6. This will be 1 over 2. Okay, this will be negative 1, 3 over 2 exponent negative 2. Where is your t is t minus 6. Okay, so plus exponent negative 3, 3 minus 6 times the step function. Okay, so from here, you change into the function definition. So from 0 to t, you use the same one, 1 over 2 plus this one. So this is the 0 to t. So this is 0 to 6. Okay, this one from 6 and above. So that's why you get the same function. And this one is much straightforward compared than the previous method. So here you have two methods for solving the differential equations. Okay. So we go for the next examples. Okay, in this case, you have the function of d square x plus dt square plus 2x plus dx over dt plus 5x plus the function ft. Where is your function from this condition? Where is your initial x naught is 0 and also x dot naught become 3. So first thing first, in this case, we want to use the step functions, the second solution, Heaviside step function concept. Okay, so the method number 2. So we know the method. In order to do this one, you can refer to example 5.36. Okay, how to do this one. So your main function will be ft. Okay, your main function is dx square over t square plus 2 dx over dt plus 5x is equal to the function. Where is your functions is the condition of t when 0, pi, and 0 above than pi. Okay, so this one is your function. Okay, this one is lesser than pi. Okay, okay, you have two conditions, two important things first. First thing first, you need to simplify the function into Heaviside step function. Okay, step function. So we know that based on this one, okay, your function will be ft t times the ht step function. So you start from 0. So t times ht naught minus t, okay, the second t times h t minus pi, because your limit is pi. Okay, there is pi here. So that's why you have this one. Okay. Okay. So what happened here? From here to here is the second condition. We know that pi is t minus pi. So you change the t to t minus pi. So then you will get something like this lah. Okay. In order to do this one, you need to go. You go for example 5.3 again. Previous 5.36. Okay. So this one. Okay, you have t0 from t to t to b. So the first one we have solved it. So ht t times ht minus t times hb, but we change to t minus alpha, t minus beta. So you will get something like this: ft t minus b h t minus b minus b h t minus b. Okay, so refresh again the 5.36. That's why you will get this one. This one. Just now, if you remember, TTH minus T minus B. Your B is, your A is 0, B is pi. So T minus B, B is pi. H, T minus B, B is pi. Minus B, B is pi. H, T minus B. So from here to here, refer example here. Refresh again. So you have this function. The next steps, okay, you need to Laplace this. Okay, you need to Laplace this one. Okay, next step. So from here, okay, from THT. So we know that is a 1 over s square minus, okay, this is 1 over s square, but the exponent negative pi s, okay, negative pi s here, internal, this one, sorry, this one, okay, minus pi, we know that pi over s is a pi over s time exponent negative pi s. So this one can be factorized, become 1 over s square minus exponent negative pi s, 1 over s square plus pi over s. You have this one. Okay, so you have solved the Laplace of the function. So first I can say solve Laplace function, okay, which is ft lah. Okay, second step will be solve Laplace of equation, okay, equation or the main equation, the x, this one. We call it, for example, we call it equation. This is equation. This one is a function. Okay. So we solve the Laplace of equation. So what is Laplace of equation? Based on this one. So the x square, I think I have taught this one. So you can simplify it. Okay. So become s square plus 2s plus 5 times xs equal to s small x naught, x dot naught, 2 naught, and Laplace, the function on the right side just now. Okay, the function of this right side ft. We already solved it in the Laplace transform. We put it the Laplace here. Okay. Then we need to solve this one lah. Then you need to put the initial conditions. So this one becomes 0, this one becomes 0. Okay, 0, 0, 0, and 3, sorry. This one becomes 0, this one becomes 3, this one becomes 0, and the Laplace. So that's why you get 3 plus 1 over s square minus the Laplace. This is the Laplace of this function. Okay. So next you simplify it to be something like this. Okay, because if each of this one will be the denominator here divided. Okay, you will get something like this. Then you need to do the this is the simplification. Next you need to do partial fraction. Okay, partial fraction. So this is the partial fractions. So you need to be good in partial fraction. So you get this one lah. But this is not the end yet. Once you get partial fraction, so this is the partial fraction, you need to inversion. Okay, the third step, I think, okay, fourth step lah. Okay, first step is solve Laplace transform. Second, solve the Laplace equation. The third, I can call it as a partial fraction. Okay, the fourth one, you need to do, what you need to do is inverse, okay, inversion from xs to xt. So when you invert this one, you will get 1 over 2 minus 2 plus 5t plus 2 exponent negative t cos 2t plus 36 exponent t sine 2t. I think refresh again, minus this one. Okay, refresh in your previous lecture. Okay, so you get this one. So this one can be simplified. Okay, simplify it. So you will get this function. So once you get these functions, so you have two conditions here. Okay. The first condition is when x is 0. Wait. Okay, you have two conditions. The first condition from 0 to pi. So this is the first condition. The second condition will be from pi and above. So from pi and from t is bigger than 5. Sorry, t is bigger than pi. Okay, so you have two conditions from 0 to pi. So you will use this function 1 over 2 5t minus 2 plus 2t, then this one. Okay, this is this one. Then from pi t bigger than pi, the second function will be put here. Okay, so then you will solve this equation. Okay, so you have two methods. The first method, the second method you have recessive function. The first method is you are doing the 1 by 1 Laplace transform lah. But the fastest one is method number 2. So if you use the method number 1 also, you will get the same one, but maybe a bit longer. Okay. So this is the differential equation of the Laplace. Okay, we go for next. Next is a transform of periodic and impulse functions. Okay. So transform of periodic function. What is the function? We have already determined the Laplace transform of a periodic function such as S sine omega t and cos omega. So we know that the sine and cos will be producing a periodic function, which are smooth and differentiable continuous function. So in many engineering applications, however, one frequency encounter periodic function that exhibits discontinuous behavior. So for example, a typical periodic function of a practical importance are shown in 5.30. So such a periodic function may be represented as an infinite series of the term involved step function. Once expressed in such a form, the result of family can be okay. So this is the example of periodic function. For example, the A1, we call it a square wave. Okay, so for example, 0 to half t become k. From half t to t become negative k. Then it keep on periodic. Okay, pattern is the same. The second, we call it as a sawtooth function, sawtooth wave. Okay, so where is 0 to t become something, we call it straight line, okay, linear. Then it keep on repeating. Okay, the third one, we call it a repeated pulse. Okay, repeated pulse. Okay, we call it a repeated pulse wave. Okay, repeated pulse wave. So repeated pulse wave, which is, for example, from 0 to k, but here there is a 0 to t, half to t, 0, then become k again, 0, and the rest. And the last one we call half wave. Okay, half wave rectifier. Okay, so this wave will come.
Doctor.
Yes. Yes.
Yeah.
Yeah.
Doctor, sekat-sekat lah, Doctor.
Ya ke?
Sekat-sekat.
Sekat-sekat.
Ngelak.
Internet.
Sekat.
Okay, wait. Sekat-sekat. Internet sini tak kuat sekejap. Saya pakai phone internet je. Okay, again, so the periodic and impulse functions. So we have square wave, sawtooth wave, repeated pulse, and half wave. It's a lot of function lah. So, but this is the one of example lah. Okay, we have this one. Okay. Okay. In order to obtain the Laplace transform from square wave illustration from the previous, so the term of solutions, the square wave may be expressed in the form of this one. So the function is ft kht minus 2 kh t minus t 1/2t plus 2 kh t minus t. Okay, plus this one is most probably the function of square wave, for example. Okay, so we have this one, for examples. Then what we need to do, we need to Laplace the transform. Okay, the Laplace each of the function in terms of we go for shift, for example, fs. So this is your constant k, 1/s minus 2/s exponent, and the rest lah. So you will get something like this. Okay, so the series inside the square bracket is infinite geometry. Progress with first term and common ratio of negative exponent, negative st. So therefore, the sum of 1/st can be expressed of this one. So this one can be simplified to become something like this. So the Laplace transforms of the square will be fs equal k/s hypotenuse tangent 1/4 st. So normally this example is proof that the following theorem, which provide explicit expression of the Laplace transform of the periodic function. Okay, this is another proof, okay, on how it works. So for example, you have a function ft defined in all positive t. It's a periodic function with period of t, big T, big T. Okay, that is, so you have t plus any constant of the big T, so equal to the functions. So when we Laplace this function ft, so we get 1/1 minus exponent negative t, integration from 0 to t, big T is exponent negative. This is the basic of if you Laplace it. So when we go for the functions, so this is the main function Laplace. So from 0 to exponent, then we solve it. Okay. So at the end, the integral will get t tau plus n/t. So the function will be Laplace of from 0 to t f t plus nt exponent negative s t n plus dt. So the function will be something periodic like this. From 0 to t will be something like this graph lah. Okay. Okay. So since the function periodic with the big T, okay. So where is your t? Ft is n 0, 1, 2, 3. So the function of this one from 0 to t is ft. Okay, this will be simplified something like this. Will be a function of lft 1/, this is, then within the tau is a dummy variable, it may be replaced by give the desired results. Okay, so this one actually in terms of Recessive function, this theorem can be simplified to be something like this. The first f1t equal to ft, this is the times the Recessive function, become ht minus, so when we Laplace this one, ft become 1 minus exponent x negative st minus 1 times the Laplace of the function. So Laplace of this, both of this. Periodic, Okay, for example, okay, for example, in figure 4.2, example using the theorem 5.1. Okay, so for the square wave, it's straight in 5 on square wave just now in this figure. Define period from 0 to big T. So where is your function of the constant of k, 0 to t of half? This is your function, and negative t one from half big T to t. Okay, so this is your first function based on the square function we wave just now. So you will get something like this: k ht minus 2ht minus 1/2t ht or minus big T. So when you Laplace this function, okay, this one is based on here, this one is based on here. Okay, remember the example 5.36, something like that. So you need to know how to do this one. So you get this function. So you Laplace this one. So you Laplace h/t will be Laplace 1/s. Negative ht minus t, Laplace of this one will become constant 2 of s exponent negative t/2 from here. Okay, plus Laplace of this one become 1/s exponent negative st. So when we simplify, become k/s 1 minus exponent t/2 square. Okay. So by using the theorem previously, okay, so we know that Laplace ft is equal k. Okay, this one is same one, 1 minus exponent t square divided by s 1 minus exponent st. Okay. So this one is equal to simplification of this one. So when you simplify this one, you will get k/s 1 minus exponent negative t/2 and 1 divided by 1 plus exponent negative t/2. So where is this one is equal to the k tangent just now. This one. Okay, from here to here. Okay. So you will get the ks is a hypotenuse tangent of 1/4st. Okay. Okay. I think we finish it until these examples. Okay, we go for example 5.44. Determine the Laplace transform of rectifier half wave. define. So half wave function is sine omega t from t is equal to 0 to pi over omega. Then the function becomes 0 when pi over omega to 2 pi over omega. So where is your ft plus 2 and pi omega equal to ft for all integer n. Okay, the solutions. Okay, so we know that the t is equal to 2 pi over omega. So we express the function of this one. So you need to change this function to the Heaviside function. Okay, first thing first. Okay, f1t in this case. Okay, what is the constant? Sine omega t. So what is the Heaviside function? So it start from 0. So mean h t. Actually t minus 0 t lah. Okay. Then minus the second limit. Okay, this is the second limit. This is the first limit. So h. Okay, what is your need? T minus pi over omega. So t minus pi over omega. So same like this. But when we change this one to this one, so see the example 5.36. So this one is become sine omega t h t. This is same. Sine omega t minus omega times function of t minus t omega. So from here you need to Laplace it. Okay, Laplace the whole thing. So this Laplace of this one will become omega divided by sine square plus omega square. Okay, the second one is exponent. Exponent based on here, exponent. So this one will be something like this. Sine omega so become omega divided by the function of s square plus omega square. So this ht minus pi over n become exponent negative s omega divided by omega. So this one, if you simplify, you will get, because you have omega same, the denominator same, so you will get omega divided by s square plus omega square 1 plus exponent negative s pi over omega. So by using the theorem previously, so what we can do is Laplace of this one is omega divided by s square plus omega of this function 1 plus exponent negative x omega divided by 1 minus exponent negative 2 omega. So this one can be simply become omega s square plus omega square 1 minus omega exponent negative s pi over omega. Okay, so means first thing first, you need to solve the Laplace of the function. Second, you need to use the theorem of wave, half wave. Theorem of impulse, theoretic. So this theorem, you need to use this one. Once you have this one, you need to use this theorem. This one. Okay, you have the Ks. What you need to do, you need to make sure your Ks become your denominator and numerator almost the same, is something like conjugate. So when this form, you can change to Ks tangent hypotenuse 1/4 st. Okay, back to here for this example. So you have this one. So you need to make sure the main denominator and numerator become conjugate. Okay, so the above become 1 plus exponent negative pi, the denominator 1 minus. So this one can become, simplify it. So you will get this one. Okay. Okay, I think that's it for today. So we will continue on transform impulse and the rest tomorrow. Tomorrow 11 o'clock at lab, computer lab. Okay. Any question?